Hello, and here's my lab on motion of falling objects. The purpose of this lab is to observe motion of falling objects, demonstrate gravity's effect on downward acceleration, reveal the effect of drag on the motion of falling objects, and illustrate Newton's second law and results of increasing momentum. Okay, now for the physics. So Newton's second law states that net force is equal to mass times acceleration. This shows that net force and acceleration are proportional, and from this you can also derive momentum, which changes throughout the object's motion. And gravity is also reliant on Newton's second law, as it is just a form of it because it's mass times acceleration, acceleration being 9.81, or the g gravity constant. And then drag, unlike gravity, is a non-constant force, and it changes based on the velocity of the object at any given point in time, and that is proportional to the b constant, which is dependent on the objects. The net force is the difference between gravity and drag. Okay, so the reason behind the laws and models for this lab. Newton's second law is important for this lab because there's always a net force acting on the object, which results in an acceleration which changes the velocity over time, and this is important to acknowledge for this lab for that reason. Momentum principle is important because there's momentum that is being changed based on the force that is always acting on the object, and this results in changes in velocity that are important to realize. And drag is also important because it's a falling object. The object is falling through air, and as a result is suffering from air resistance, which creates a drag force which slows the object down. Well, doesn't necessarily slow it down, but it decelerates the object. Gravity is the force that is constantly accelerating the object, while drag is slowly counteracting it. And terminal velocity is important to know because that is when drag and gravity are equal, and therefore the velocity will stay stagnant because there's no acceleration, because there's no net force. Tracker and glow script are what we use to track the observed object and then simulate it in computational models. So the results. Results differ when drag force is and isn't incorporated into the model. When it isn't, the model is inaccurate, but when it is, the model is fairly similar to observed motion. And drag plays a significant effect in falling motion of objects, depending on the objects that are being used. Some objects may have small b values, so it can be fairly negligible, but others have larger b values, and the drag is much more significant. So the system, the surroundings was the dorm lounge that we did the experiment in. The system itself was a puzzle box, which was also the mass. The position is where the box is released initially, and where it is along the y-axis until it touches the floor. Gravity causes initial motion and acceleration, but drag lowers this acceleration over time until that that acceleration approaches zero. The initial velocity is 0 meters per second, and the initial position is 5 feet, or 1.524 meters. The b value is 0.85, which we gained through guessing and comparing the simulations with the observed thing. Here's Tracker. So this is the video that we used for the project. You can see that we put data points at each point in the box's motion, and then those points were plotted onto this graph. And then this shows all the data points we got from that, which we put into the graph that compares all. After tracking the observed object, we made two computer simulations, one where drag is not taken into account and one where it is. Here you can see that because b is equal to 0, drag is not taken into account in our functions down, or our calculations down here. And so as a result, there is constant acceleration. The velocity versus time graph is straight, and it continues to accelerate downwards. In our other simulation, we did take drag into account, and as you can see, drag is the b value is not 0, it's 0.85, and drag actually matters in our equations down there. And here you can see that the velocity versus time graph is curved, and the position versus time graph doesn't always accelerate. It starts accelerating, and then it deaccelerates down here. So this is the graph we got from the models and the tracker. So here you can see the tracked position and the drag and gravity simulation are pretty similar, while the only gravity simulation went much further. So the similarities, we see some similarities in that they have the same starting point and they all accelerated downward, and the second simulation graph is very close to the observed one. However, the difference in displacement is a major difference because the first simulation goes much further than the other graphs due to drag not being taken into account, and velocity flattens for the second simulation and the observed graph. There's also a lot of more variation of data in the observed graph due to human error. So possible sources of error: first, human error in tracking, which was said before, an inaccurate b value because the b value is determined through guessing and checking, not through a concrete method. And the camera angle may have also altered our results a little bit, and we were also unable to measure the mass of the object, which in most cases would not matter due to the Newton's second law and gravity having the same acceleration no matter what, and drag force not taking into account mass. Which models predict terminal velocity? Well, the observed object in the second model, including drag, both show terminal velocity as net force approaches 0 as drag approaches gravity, and as a result, the acceleration approaches 0. The velocity is also getting closer to becoming constant as the object progresses in its motion. Now, what if the object has an initial velocity due to being thrown downward? The terminal velocity would remain the same, as the terminal velocity is determined by when drag force is equal to gravity, and this would result in a larger initial drag force due to there being a larger initial velocity. And this large initial drag force would result in the object having less acceleration due to the net force being smaller in the negative direction. And as a result, there'd be less acceleration, and the object will reach terminal velocity quicker due to the drag force already being there at the beginning, and as a result, both the terminal velocity will stay the same in this object. The initial velocity has no effect on a terminal velocity. And we can see from this graph here that the non-zero initial velocity and the no initial velocity both approach the same point at the end of the day. Just one of them reaches that terminal velocity quicker than the other. So conclusions that we can draw from this are drag force has an immense effect on real-world falling objects, and results differ when drag force is and isn't incorporated into a model. Drag force eventually cancels out gravity, creating constant velocity, and this is called terminal velocity. Initial velocity has no effect on terminal velocity, however, as only the gravity and drag constant affect it, and incorporating drag force into models makes them more accurate in the event of real-world falling objects.